So we've got an Automation Direct GS1 variable frequency drive that's powering up a quarter horsepower three-phase motor. We are currently measuring the voltage being applied to the motor with a fluke voltmeter. We're reading 265 volts, that's phase to phase, or line voltage applied to the motor, 265 volts at 60 hertz, right there. So you can write those numbers down. We can actually calculate volts per hertz. And if we do that, go ahead and get your calculator out, do a quick calculation.
Okay. Yeah, it looks like at 60 hertz, 4.4 is our VF.
Oh yeah, we calculated that earlier. Okay, so I'm going to take this and lower this to 50 hertz. Right there. Of course, only on video can I have trouble setting it to 50. There we go. Close enough. 50 hertz. Over here, 228.5 volts. You notice the drive decreased the applied voltage to the motor as I decrease frequency. It's trying to maintain a fairly constant volts per hertz relationship. If I decrease this even more, down to about 30 hertz, that should be about half of what it was before. How many volts do we have at 60 before? 200 and something?
264.
264, so now we have 124 volts, about half of what we had before at 60 hertz. So at 30 hertz, right there, 124 volts. We turn it down even more. I'm going to go to, say, 10 hertz. Of course, the frequency is primarily what drives a motor at different speeds, but we have to reduce the voltage as well with frequency so that we don't overpower the windings of the motor at those lower frequencies. As we decrease frequency to the motor, the inductive reactance of the motor windings decreases as well. If this were to maintain a constant voltage output with a decreased reactance, that would result in vastly increased currents at low speeds, and that could burn the motor up potentially, or saturate the windings. So what's happening here is it decreases the voltage in proportion to frequency. They call it the V to F ratio, or the volts to hertz ratio. And what do we calculate there for V to F? Is it like 4.6 volts
It's
per hertz?
4.6.
Yeah, and it's almost a constant 4.6 volts per hertz, looking at that table right there, about a constant 4.6 volts per hertz. It's calculated with the different voltage readings and frequencies that we got in this particular setting. Now, we can also configure different profiles for the volts to hertz ratio in the drive. What we're looking at here is just one of the available profiles. You could set this up, for example, for a high starting torque application, in which case it's going to give a greater volts per hertz at lower end than at high end. So right here, this is the numbers we got here for our high starting torque. We got a 12.3 volts to hertz ratio at 10 hertz, and then as we sped the thing up, we finally got up to 60 hertz, it dropped back down to normal 4.4 volts per hertz ratio. This gives increased or boosted current at the lower end of the speed range, and that results in higher torque at lower speeds. Certain loads, like reciprocating air compressors or conveyors or something like that, may require the increased or boosted torque at the low RPMs. Other loads are just the opposite. They require higher torque at the full speed and lower torque at the low speed. For example, turning a fan or a centrifugal pump. As the impeller turns slowly, it doesn't need a lot of torque. And so there's an application you can program the drive to put out less volts per hertz at the lower end and reduce the amount of current to the motor, and thereby cutting down your power consumption, your heating in the motor, and your torque, because you don't need it for those sorts of loads.